Today I'm going to talk to you a little bit about enthalpy, which is a concept we began in honors chemistry, so we'll elaborate on that a little bit in AP, and then we're going to talk about calorimetry, which is one way that we can measure enthalpy. So first, what is enthalpy? So enthalpy is a quantity that has the symbol H. We in this class are only really going to ever refer to delta H, which is the change in enthalpy for a given process. And there's a long, complicated definition about internal energy and pressure and volume, but what you need to know about enthalpy is that enthalpy is just the heat in the reaction if it's done under constant pressure. And so why would it be useful to have a measure that's under constant pressure conditions? And that's really because we do almost all of our chemistry in the lab at atmospheric pressure. So our pressure stays constant throughout the course of a reaction. So it turns out that delta H is a really useful quantity to measure the heat that's transferred in chemical reactions. Now, if we're going to go over two terms that you know or should remember from honors chemistry, exothermic. Exothermic reactions are reactions that have a negative delta H. That means that the system actually produces heat, and so the surroundings absorb heat in that process. An endothermic reaction is the opposite. An endothermic reaction has a positive delta H, and that means that the system is actually absorbing heat in order to move forward, and so that heat has to come from the surroundings. And so one thing I just want to touch on is to make sure that you understand where that energy is coming from and where it's going. So there are two types of energy in a chemical reaction or in any system: kinetic energy and potential energy. In chemical reactions, the kinetic energy is thermal energy, which we talked about before, and that's just what allows the molecules to move around. And then the potential energy in a chemical reaction is all energy that's stored in the bonds. So that energy is released or absorbed when we make or break bonds, and so that's where that energy is coming from or going to when these reactions occur. And this will become clearer as we start to do some calculations and you see how that energy actually changes as we break or form bonds. So following from that, we can now think about bond energies and whether our reaction is going to have a positive delta H or a negative delta H. So when we think about bond energies, you want to think to yourself that breaking bonds is going to require energy. And therefore, from the law of conservation of energy, anything that we would form would give us energy back. So in a reaction, it's going to take energy to break our bonds and our reactants, and we'll get some of that energy back when we form new products. So if delta H is negative, then that means that the bond energy in the products is greater than the bond energy in the reactants. And so we're going to get more energy back when we form those new compounds than we required to break the old ones. So, and if delta H is positive, then the bond energy in the products is less than the bond energy of the reactants. All right. So as a general rule, nature prefers to move toward a state of lower potential energy. So with that in mind, you can know that the type of reaction that's going to be spontaneous would be one where we have more energy stored in the products than we did in the reactants. So that's going to be when we have an exothermic reaction or when delta H is negative. Hopefully you also remember from honors that we can use the delta H of a reaction along with the coefficients in our equation to figure out how much heat is transferred for a given amount of reactant or product. And so, just in case you don't remember, here's an example, and we'll do a few in class as well. How much heat is released when 0.500 grams of propane, which has a molar mass of 44.097 grams per mole, is combusted completely? Okay, and then the reaction is above, it's balanced, and the delta H of the reaction is given as negative 2,044 kilojoules. All right, so since this number is negative, that tells us that heat is going to be released. It's going to be an exothermic reaction. And now we can just set up our dimensional analysis and use stoichiometry the same way that we would if we were just converting from moles of one product to another. What we're given is 0.5 grams of propane. All right, and that's going to be our number out in front. And then we're going to multiply that times 1 mole over 44.097 grams, because that's how much a mole weighs. And then we can look at our balanced equation and see that the coefficient for propane, which is C3H8, is just 1. Okay, so that's going to be our number on the bottom here. If we were given the amount of carbon dioxide or something, then we would use the 3, which is the coefficient for CO2. And then on the top is just going to go the delta H for the reaction, which is 2,044 kilojoules. And the reason I'm not including the negative is because the question asks us how much heat is released. So that takes care of the negative. All right, so if we do 0.5 times 1 over 44.097 times 2,044 over 1, that's going to give us 23.2 kilojoules that are going to be released when that amount of propane reacts. Now we're just going to take that knowledge and apply it to a real experimental situation. And we're going to do these in the lab ourselves as well. So these use a very simple apparatus called a coffee cup calorimeter, which is just what it sounds like. It's 2 styrofoam coffee cups, one inside the other, and they serve as really great insulators. And so there's a really cheap and easy and a relatively accurate way to measure how much the temperature changes when a given reaction occurs. So we can use the knowledge that we talked about in the last lecture, where if the reaction is our system, then whatever heat is released or absorbed has to either go into the surroundings or come from the surroundings. So our Q reaction is going to equal negative Q of our solution if we're measuring the change in temperature of the solution where a reaction is happening. So to do an example of this, just to make it a little bit more real, what is delta H of the reaction for the reaction below if 0.125 grams of zinc metal reacts with 75 milliliters of HCl, which is in excess, and the solution temperature increases from 22.3 degrees Celsius to 23.27 degrees Celsius. So before we do any calculations, you should have already figured out that Q for our reaction is going to be negative because our temperature is going up, which means that our reaction is releasing heat into the surroundings. Okay, so if Q of the reaction is equal to negative Q of our solution, then that's going to be equal to negative the mass of the solution. So our solution just contains 75 milliliters of water. So we know that 75 milliliters weighs 75 grams. So that's going to be our mass. Then times the specific heat capacity for water, or for HCl, but it's the same as water, which is 4.18 joules per gram degree Celsius, times the change in temperature. And if our final temperature is 23.27, our initial temperature is 22.30, that gives us a temperature change of 0.97 degrees Celsius. All right, so then we can just multiply those numbers out, and we get the Q for the reaction is negative 304 joules. All right, so that just tells us how much heat is released for this specific reaction, but what we really want to know is what's the heat of the reaction in kilojoules per mole, because that would let us apply it to any amount of reactants. So in order to do that, we have to know how many moles of reaction happened above. And you can see from your balanced equation that 1 mole of zinc reacts in each mole of reaction. So all we need to do is figure out how many moles of zinc reacted. All right, so if we have 0.125 grams of zinc, we can just use the mass of zinc from the periodic table. So we'll do that times 1 over 65.38 grams. And that gives us 0.00191 moles of zinc. Okay, so our Q of our reaction is negative 304 joules, and that's how much we got per 0.00191 moles of zinc, or that many moles of reaction as well, because it's 1 to 1. So we can literally just divide these two numbers to get the delta H for the reaction, and we can easily convert from 304 joules to 0.304 kilojoules because there are 1,000 joules in a kilojoule. Right, and when we divide those two numbers out, we get negative 159 kilojoules per mole, and that would be the delta H of our reaction. So like I said, we're going to get to do some of these calculations in the lab later in this unit.